तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we saw the importance of learning about electronics, the method of learning by doing, how it is very useful in learning a subject like electronics, and the brief history of electronics about the various stages like the vacuum tubes, the transistors, and the integrated circuits. We also saw the plan of the topics to be learnt during this lecture, how to build circuits using breadboard, and some ideas about the use of digital multimeter and power supply, which we would be making use of in doing different experiments in electronics. The plan, again I try to tell you, is to read about three aspects in electronics. Basically, the components and devices, the measuring instruments, and the different circuits. Under components and devices, passive components like resistors, capacitors, active components like transistors and operational amplifiers, measuring instruments like digital multimeters, power supplies, current sources, oscilloscopes, etc., and circuits like rectifiers, amplifiers, oscillators, etc. Let us first start with resistors. What are resistors? They oppose the flow of electrons basically, or in effect the current. So resistors resist, as the name suggests, the flow of electrons or the current. The symbols of resistors are shown on the screen. You can see there are two types. Many people use different type of symbols, any one of them, and resistance is generally measured in units called ohm, OHM. 1000 ohm is also known as 1K. It's written as 1 kilo ohm or 1K, which is equivalent to 10 power 3 ohm or 1000 ohms. Similarly, 1000 kilo ohms is also shown as megohm, which is equivalent to 10 power 6 ohm. Resistors can be broadly divided into two types. One is fixed resistors and the other is variable resistors. Fixed resistors means the value is fixed, it will not change during the use, whereas variable resistors, the value of the resistance can change while being used in different circuits. One of the well-known examples of fixed resistors are carbon film resistors. They have about 5 to 10% tolerance mostly. We will explain more about what we mean by tolerance. And metal film resistors are also very popular these days. They have much better tolerance, 1% to 2%. And lastly, wire wound resistors, where it is the wires which are used of different lengths for generating different values of resistors. Fixed resistors is one, as I already mentioned, for which the value of the resistance is specified and cannot be varied in general while in use. The resistance value is displayed using a color code or a color bar, as the case may be, because the average size of a resistor is too small for the actual numbers to be printed on them, and therefore, we use different color codes which are actually rings of colors having different numbers as codes. The resistance value is a discrete value. For example, you would come across values like 1, 2.2, 4.7, 10, etc. in a typical situation. I have given an example here of a carbon resistor. You can see there are a number of bands of colors all around. It's something like a cylinder. You can see there is a brown here, black, orange, yellow are the 4 color bands that we have here. The brown, the first line, corresponds to number 1, it's equivalent to value 1. Black has value 0, orange has value 3, and therefore, this is 1, 0 into 10 power 3. The third band is corresponding to the number of zeros that we should add, or 10 power 3. In this case, 10 into 10 power 3, which is equivalent to 10 k ohm, 10 kilo ohm, 10,000 ohm. The last band, the fourth band here, is actually the tolerance band. It tells, for example, how much the value of the resistance, fixed value of the resistance, can vary, and here the gold strip here is corresponding to plus or minus 5%. So the tolerance here is plus or minus 5%, and the value of resistor is 10 kilo ohm. Here I have given a table of all the color codes. For example, black, brown, red, orange, the colors of the VIBGR, plus some additional colors like white, etc. are all included here, and the corresponding value is listed in this column in the table, 0, 1, 2, 3, 4, 5, etc. up to 9, and this is the multiplier, which is a 10 to the power that you normally specify. You can have 0, 1, 2, 3, 4, etc., which is almost same as the previous one. And the last column shows the tolerance. For brown, when you have a brown ring, it corresponds to plus or minus 1%, or red for plus or minus 2, etc. These are the color bands for tolerance values. Now I will also show you one other example, a second example, where you can see there is a yellow, violet, black, red, and brown. This is a 5-band resistor. The 4 bands corresponds to the value. The last band, brown, as you can see here, corresponds to tolerance, which is plus or minus 1%, as we also saw in the table. Now the value of the resistor is obtained by looking at the corresponding code for the colors. Yellow, for example, is 4, violet is 7, black is 0, and therefore 470 is the value of the resistor, and the red is actually the power of 10, and that is 2, and therefore 10 power 2, which gives a value 47,000 ohms, or 47 kilo ohm, and the tolerance is plus or minus 1%. So by knowing this color code, one can easily understand the value of a given resistor, and he can decide to make use of them in the different circuits. Now let me explain a little more about the tolerance. The tolerance of the resistor is also a very important property of the resistor to consider in very different applications. For example, a 100 ohm resistor with a 10% tolerance means that its value can be any fixed value between 90 to 110 ohms. 10% this way or that way of 100 ohms, which corresponds to 90 to 110 ohms. That means if I pick any resistor from a 100 ohm bunch, a bunch of resistor which are marked 100 ohm, if I pick it up, it can have a value anywhere between 90 ohms or 110 ohms. Similarly, a 120 ohm resistor, for example, with same 10% tolerance, can have values anywhere between 108 to 132, which is again 10% either way, this way or that way, of 120 ohms. Thus the upper limit, you can see, of 110 ohms of the lower value corresponding to 100 ohms, and the lower tolerance limit of 108 ohms of the upper value 120 overlap. So that is how the choice of resistances to manufacture are decided, so that each resistor value, its lower limit and the upper limit overlap with the next value of resistor. That is the reason why you have different numbers like 47, 33, 22, etc. coming into the manufacturing of resistance. So hence resistor with a value between 100 ohm to 120 ohms can be obtained from either of the two sets of 100 ohms or 120 ohms. Most of the times the value of resistance in a given circuit is not very critical in the performance of the circuit. A small variation in resistance will not bring about any major variation in the performance of electronic circuits most of the time, except there are some special cases where you have to have very precise value of resistors introduced. Similarly, a resistor value between 120 ohms to 150 ohms can be obtained from either of the two sets 120 ohms or 150 ohms. So the resistor values of for manufacturing under 10% tolerance are chosen such that the upper limit of the lower value and the lower limit of the upper value overlap, so that one need not manufacture the intermediate values of resistance. Now I show you, for example, the 10% what all the values normally manufactured: 10 ohms, 12 ohms, 15 ohms, 18, 22, 27, etc. Now this can be ohms. For example, I can add another 0, for example here 100 ohms, 120 ohms, 150 ohms also manufactured, 1000 ohms, 1200 ohms, 1500 ohms, etc. are also manufactured. 10 kilo ohms, 12 kilo ohms, all values of resistors in different denominations will be manufactured, having values only what is shown in this column of the table if they belong to 10% tolerance value of resistance. If I go to 5% tolerance, obviously you can see the overlapping will be limited, and therefore have to introduce more number of values in between, so that the intermediate values can be obtained from any set of these values of resistors. So the 5% tolerance will be manufactured for more number of preferred values, as you can see in this table. Now let us look at carbon film resistors. These are most general purpose and very cheap in terms of cost. Usually the tolerance will be around plus or minus 5%, and they are manufactured with different power ratings. For example, 1/8 of a watt, 1/4 of a watt, half a watt are frequently used in many electronic circuits. Of course, there are some disadvantages using carbon film. Mainly they tend to be very noisy. So these are, the figure shows some of the examples of resistors, carbon film resistors. You can see they have different sizes. This one is very small, this is slightly bigger, this is much bigger. So this is, for example, 1/8 watt, this is quarter watt, and this is half a watt. So you do have resistors with higher wattages, and the resistors with the higher wattages will be bigger in size in general. We will discuss more about what we mean by the higher wattage value and things like that. Then there are other type of resistor, for example metal film resistors, which are very, very useful. Metal film resistors are used when you require much closer tolerance. They are very more accurate in value, and usually nichrome, which is a alloy of nickel and chromium, is used for the material of the resistors. They are much more accurate than the carbon film resistors. They have about plus or minus 0.05% tolerance. I have given here the photograph of metal film resistors. By physical appearance, they don't find to be very different from the carbon film resistors, but then in terms of performance, these resistors are much better. And as I mentioned in the other case, the different sizes here corresponds to different wattages. There are other resistors, for example wire wound resistor. The wire wound resistor is basically a long wire of a very specific resistance value, which is wound on a insulating former, and then the resistance value can be generated to any precise value. So high wattage resistors in general are made of thick wire material. Usually wire wound resistors are used for higher wattages. But wire wound resistors cannot be used for high frequency circuits because of the associated inductive values, inductances. For example, these are some of the wire wound resistors. This is actually 660 ohms. This we are not able to see. It should be around 10,000 ohms or something like that. Wire wound resistor. They are wound on a ceramic base over which the wires are wound. The next type of resistor is ceramic resistor. These are again wire wound resistors, but cased in a ceramic encasing, so that they can have much higher wattage, higher power rating, where they have 1 to 2 watts or sometimes even 10 watts and 20 watts. You can have wire wound resistors which are encapsulated in ceramic encapsulation. These resistors can become extremely hot because they are meant to be used at very high wattages, and therefore one has to take care of these resistors when they are being used. For example, this is the ceramic resistor. Inside you would see there will be a wire wound on a ceramic former, and that is completely enclosed in a ceramic encapsulation. There are some more resistors which are used in modern circuits. They are the concentration there used to make them very, very tiny, small, and then they will almost look like a small integrated circuit IC. So it is made with many resistors. They are called resistor arrays or network resistor, single in line, and they have one resistor or multiple resistors, connected or disconnected. Different types are there. For example, they can be used whenever we use light emitting diodes to control the current through the light emitting diodes. These single in line network resistors or array resistors will be used, and the value of the resistor will generally be printed on them. I have here an example of a single in line resistor, and the corresponding arrangement is shown in detail on the right. You can see that, for example, the resistors are all here and they are all connected at one end, and the common terminal is provided, whereas the other end is available for us to use in different circuits. So usually, for example, they have 9 leads, 8 resistors, all of them having one common, and rest of the 8 leads are given here. So this is one type. There are also other type, for example 4S resistor network, where the 4S indicates the package. It contains 4 resistors. So each one of the resistors independently given, unlike in the previous case. You can see there are 4 independent resistors, but all of them encapsulated in one piece, and therefore you can use them in different applications independently. When you want large number of resistors, instead of buying independently different resistors, you can buy a single package in which 4, 5, 6 independent resistors are provided, and this can be used in a compact way in different circuits. Now we will come to variable resistors. There are 2 general ways in which variable resistors are used. One is where the value is to be changed during, for example, the operation. The normal example is the volume control in the case of an ordinary radio receiver. The volume control is basically a variable resistor, and when you move it or turn it round, you would find the volume will increase or decrease depending upon the direction of rotation. There are other semi-fixed resistors that is not meant to be adjusted by the user, by anyone other than a well-trained technician. It is usually to adjust the operating condition of a circuit by a technician. So it will not be accessible most of the time to the user, but it will be inside the circuit. The technician will set it up and then slightly vary to the preferred value that he would like to have and set it at that stage. Nobody will be able to change it beyond that. These are called preset variable resistors. The other one is called potentiometers. The semi-fixed resistors are used to compensate, for example, the inaccuracies in resistors. You won't be able to get very precise value, and then you can use this type of a variable semi-fixed resistor and set it to a fixed value for fine-tuning a circuit. The rotation angle of most of the variable resistors will be around 300 degrees. Some variable resistors must be turned many times. These are called multi-turn potentiometers, multi-turn pots for short. To use the whole range of resistance, you have to turn several times, not just one rotation, but maybe 10 turns or 20 turns, as the case may be. So for example, if the value of the resistor is 10,000 ohms, if you have to rotate the knob 10 times, then you can see for each rotation the variation in resistance will be rather very small. So the resistance will be very slowly varying. Therefore you can set any precise value appropriately. These are called either potentiometers or trimmer potentiometers or presets. I have shown here in the picture number of variable resistors. This one is a very big variable resistor with a knob here which can be rotated. The all variable resistor will be characterized by 3 terminals, 1, 2, 3, and this one is actually these all the 4 in the center are preset potentiometers or trimming potentiometers. They are used for setting precise values by the technicians that I already mentioned to you. These two, they are the left end are multi-turn potentiometers. There is a small screw here which can be rotated, and depending upon the number of rotations that you give, the value of the resistance will change. There are 3 terminals in all the cases, as you can see, but for a variable resistor we will use only 2 of the terminals. The value between the 2 will only change. If I choose the extreme ends, usually the resistance value will not change, it will be fixed. That can be understood by looking at the construction that I have shown in this picture. For example, there is a terminal A, there is a terminal B, and this is the carbon composite or whatever which is used for the resistive material, and this the center one is actually called the wiper. This wiper can be moved on along the periphery of the resistance value, and so that if I take for example between terminal A and the wiper, the value of this only will be included in the circuit, therefore the resistance will be this much. Whereas if in this figure, if I use the same center on terminal A, it has got much larger portion of the resistance, and therefore the value of the resistance will be much higher. So this wiper can be moved throughout by around 300 degrees, and thereby I can vary the resistance value. Therefore you can understand that the variable resistance will have to be using either this wiper and any one of the other 2 terminal only, either A or B, not both. So this is about the variable resistance. This graph gives you the change in resistance as we change the rotation angle clockwise. For example, this is the resistance value. There are 3 different types, A, B and C. In the case of B, you find the resistance changes linearly by precise value with the rotation angle. This is called a linear potentiometer. Whereas the curve corresponding to A shows initially the resistance varies very slowly, and then the resistance varies very fast with large values. In the case of C, it is the other way about. First resistance changes very rapidly by large values, and as I come to larger angles, you find the resistance changes very slowly. All the 3 types are there, but most of the time we use only A and B in many applications. Now we will come to a different type of resistors. In resistance there are different types. For example, here is one type which is called light dependent resistor or LDR. Some components can change resistance value by changes in the amount of light falling on them. One type is the cadmium sulfide photocell, cadmium sulfide resistance actually. It is a kind of resistor whose value depends on the amount of light falling on it. When you keep it in darkness, its resistance will be very, very large, and as more and more light falls on it, the resistance becomes smaller and smaller, because it is basically a semiconducting device. I have shown you this construction of a light dependent resistor. You see this is the cadmium sulfide portion, and you can see the circuit symbol is normal resistor symbol with a circle and external arrows showing the light falling on them. The circle shows that they are conditioned by some parameter, in this case the light. This is a circuit symbol. Now this is actual photograph of an LDR. The typical case of LDR is around 8 millimeter in diameter, 4 millimeter in height, and it is in the form of a cylinder. When bright light is on it, it will be around 200 ohms, and when in darkness the resistance can be more than 2 megohm. Similarly, there is another type of variable resistor which is a special type which is called thermistor. These are thermally sensitive resistor. The LDRs are light sensitive resistor, the thermistor is thermal sensitive resistor. Thermal means temperature, that means heat sensitive resistor. Therefore, they can be used for measurement of temperature. The resistance value of a thermistor changes according to temperature, and therefore they are used as temperature sensor. There are in general 2 types of thermistors. One is called negative temperature coefficient, and the other is called positive temperature coefficient or PTC. The NTC shows that when the temperature increases, the resistance decreases. That is corresponding to NTC. The positive temperature coefficient means when the temperature increases, the resistance increases also. So there are two different types, and they can be used for temperature sensing. This is a figure of a thermistor with the two leads, and its resistance will be dependent on temperature, as I already mentioned to you, and approximately the equation representing a thermistor can be seen on the screen. Or the resistance at any given temperature will be equal to R0 exponential some constant beta times 1 by T minus 1 by T naught, where T naught is a reference temperature and R naught is the resistance of the thermistor at the reference temperature T naught. So at any given temperature T, the resistance will change according to this exponential relationship, and therefore you can see as temperature increases, the resistance will also increase in this case, or depending upon whether it is NTC or PTC. We have seen different types of resistors like LDR and thermistor. In general, resistors are also rated for the power dissipation. For example, when the resistors are used in any given circuit, due to the current flowing, there will be a heat generated, which is called the Joule's heat. And so for a given current, if I keep on increasing the current for a given resistance, the heat generated can become so large, then the resistance can be damaged due to the heat generated. Therefore, there is a maximum power rating for any given resistor, which should not be exceeded in any given circuit. So the maximum power rating specifies what is the maximum current that we can pass through the resistor. They are specified usually in watts. The power is calculated using the square of the current I square R, as we all know, where R is a resistance value, I is a current. Resistors, as I already mentioned to you before, comes in different rated values like 1/8 watt or 1/4 of a watt, half a watt, 1 watt, etc. For example, when we power light emitting diode, usually LEDs require just 1 or 2 volts to operate, but you may be connecting to a 5 volts or 10 volts power supply. Then you should try to put additional resistors to drop the voltage, total voltage 10 volts to some 2 or 3 volts, what is required to only to be applied across the LED. We will see more of that later. But these resistors, when you want to drop down some voltage in a given circuit, will have to be carefully worked out on the basis of the power rating that you can think of. For example, I have a 12 volts power supply which is to be used for powering an LED or as a given circuit which requires about 100 milliamperes of current. So the circuit requires only 5 volts, it requires 100 milliamperes maximum current, and that means 12 minus 5, the extra 7 volts will have to be dropped in some resistance. How to calculate the resistance? It can be calculated using voltage by current gives me the resistance. Therefore, 7 volts divided by 0.1 ampere or 100 milliampere is equivalent to 0.1 ampere, and that corresponds to 70 ohms here. And therefore, I must try to use a 70 ohm resistor in series with my circuit, which requires only 5 volts when I apply a 12 volts power supply. The consumption of electric power will have to be worked out by using I square or formula, in this case 0.1 ampere into 0.1 ampere into 70 ohms, which is just about 0.7 watt. Therefore, in general, if it is about 0.7 watt, it is better to use about twice the value as the actual safe value of resistance. So if you use 1.5 or 2 watt resistor, it will be good enough. So the selection of resistors therefore depend upon 2 factors. One is the tolerance, the other is the power rating. Now to go to the working table, and I will show you some of the real resistors, and I will try to measure the value of the resistors, and I will also show you the light dependent resistor and the thermistor. For example, here you can see resistors with different wattages. These are actually different wattages. This is about 1/8 watt, this is quarter watt, this is half a watt, this is 1 watt, this is about 10 watt. This is a ceramic resistor that I mentioned to you. And apart from, you can see the sizes are also increasing corresponding to the value. Some of the values are almost same. For example, this is 1000 by the color code, this is also 1000, I think this is also 1000. So many of the resistors are all of the same value, but the size is different because they are used for different higher wattages. Next I have here, for example, a potentiometer that I already mentioned to you. I have a knob here which I can turn, where which I can vary the value of the resistance. So you have 3 leads here which are connected here. I can measure the resistance using a multimeter. Here I have number of fixed resistors, as I already shown you also. These are actually chip resistors or single in line resistors. These are different wattages. Here I have number of variable resistor. For example, this is a trimming resistor, this is again a trim pot, this is a variable resistor with a carbon, this is a linear potentiometer. The variation can be changed by moving it along the line, and these are variable resistor where the rotation angle will decide. This is again a multi-turn potentiometer. You have to turn this multiple times to vary the resistance. Now here I have connected one variable resistor and I have connected in a breadboard corresponding to. The green one is the center, and I have used one of the center and one of the other terminals, and I have connected to a multimeter. Now you can see the resistance is around 354 ohms. Now I am going to change the value of resistance by changing the knob, and you can see the value of the resistance also changing there. Therefore, the value of the resistance can be changed by using this type of potentiometer. Next, I am going to show you a light dependent resistor. This one is a cadmium sulfide light dependent resistor. This one is a thermistor, which resistance value will depend on temperature. Now I am going to show you this example by connecting 2 wires. I am going to change the amount of light falling on it and measure how the resistance is changing with reference to light. Now you can see I have connected it to the multimeter. It shows something like 400 it is very small value, some 450 to 500 ohms. Now I close the light falling on it, then you can immediately see in the dial the resistance becomes very large. It is around 4 point some K. Now if I completely hide it with a very opaque material, the resistance will still go higher. Now I remove my hand, you can see the resistance again comes down to some few ohms, and when I close it goes to very high value of the order of several kilo ohms. Actually when I completely close it, it will go to very high values equivalent to megohms. Now next I want to try looking at the variation of resistance with temperature. I have again connected the 2 ends to the multimeter. It is showing some 12 kilo ohms right now. I am taking a soldering iron which is very hot, and I am going to touch the thermistor. Immediately you can see in the display the resistance keeps coming down, 5K, 4K, 3K, 2K, etc. Now if I remove the heating, then again you would find the display slowly climbing up to the original value of about 12K. Now it is already 4K. It is becoming larger, and as I cool the temperature will is falling down, and therefore the resistance will increase. So I have here shown you all the different type of resistors, and both fixed and variable resistor, and special type of resistors like LDR and thermistor. Now we will go on to a very important law which relates the resistance. For example, the voltage, current and resistance, they are related by a law which is called Ohm's law. This is very, very important fundamental law, most of you might already know, and what Ohm's law states is that the voltage, when I apply across a conductor, the current produced due to the voltage will be proportional to the voltage applied. V is proportional to I, or V is equal to I into R, where R is a proportionality constant which is called resistance. So, this of course is true only for a given temperature. As the temperature we have already seen, every resistor when the temperature changes can change its resistance value, that is called temperature coefficient. That is why I called the NTC and the PTC, the negative temperature coefficient and the positive temperature coefficient, with reference to thermistor. R is of course called the resistance and in measured in ohms, that also I mentioned to you, and usually it can be in ohms or kilo ohms or mega ohms. And there are other useful relationship that we get with corresponds to, for example, V is equal to I into R or R into I, and R is equal to V by I. You can see the V, I and R are related by three different relations. V is equal to I into R, I is equal to V by R, and R is equal to V by I. Here I have much bigger plot where I also make use of the power rating P, the current I, the voltage E, and the resistance R. All of them are related by different relationship. Depending upon what you want in a given situation, you would be making use of all these relationships. Now let me quickly explain to you about Ohm's law. For performing a verification of the Ohm's law, you require a battery, you require a current source, current meter, and you have a voltmeter and a resistance. So if you look at the circuit diagram, you have a battery, you have a current meter, you have a voltmeter and a resistance. The battery, current meter and resistance are connected in series, and the voltmeter is connected across the resistance to measure the different voltages. Now if I vary the voltage of the battery here, you would find the current will increase when I increase the battery, and the correspondingly you will see the voltage measured across the resistance will also increase. That is what Ohm's law says. Now we will quickly go on to verify Ohm's law in an actual case on the table, and then we will come back to the rest of the things. So now here I have a circuit. There is a resistance here which is I think around 10 kilo ohm, or I think 10 kilo ohm I think, and you have a voltmeter here, ammeter I should connect. I have an ammeter, so I am connecting the ammeter now. I am connecting the voltmeter, to the positive end to the red, negative end to black. So I have connected the voltmeter which is here and the ammeter which is here. I will switch this on and bring it to current, and I want DC current, therefore I will press the yellow. Now this measures DC current, and this I should switch it on to measure voltage, and I want DC volt, so I press again. This is now measuring DC volt, this will measure current. Now I will switch this on, and I have connected the battery to the input here. Now let me slowly increase the voltage. So you can see the voltage is around 9 volts and the corresponding current is around 9.5 milliamps. If I reduce the voltage to some 4.4 volts, the current also is around 4.5 milliamperes, or my 4.5 milliamperes. Now I again still decrease to around 2 volts, 2.32, and you can see the current also is 2.36. Therefore you can see the voltage as I decrease, the current also decreasing. When I increase the voltage, the current also increases. Now you can see I am increasing the voltage to around 5.5 or so, and the corresponding current also is increasing to 5.5. Therefore the resistance, when it is in the circuit, the voltage and the current are proportional. Voltage is equal to I into R, the resistance that I have included here. The resistance incidentally is around 10 kilo ohm, 1 kilo ohm, I think 1 kilo ohm. Now we have seen Ohm's law, where we have used a very simple circuit using a battery, a current meter which is actually a multimeter used in current mode, and a voltmeter which is again another multimeter used in the voltage mode, and I have used 1 kilo ohms resistance in the circuit, and by varying the voltage, the current and the voltage was shown to vary proportionally, and the proportionality constant is actually the resistance R in the circuit. I have tried with 1000 ohms, but we can also try the experiments with different resistances, and we would find the Ohm's law is verified. But the Ohm's law is verified only for resistances which are fixed value, not for the special resistance that I mentioned, for example the light dependent resistor or the thermistor, because their resistance also depends on another parameter which is either light or temperature, and therefore unless you maintain your constant light intensity in the case of LDR or your constant temperature in the case of thermistor, they will not obey normal Ohm's law. So one has to precisely set that light intensity or the temperature as the case may be, and then only verify for such resistance, special type of resistances. There are also other type of resistance like voltage dependent resistor, VDRs as they are called. I did not mention to you or I did not show you, but VDRs are generally used for protection in a circuit. Their resistance will depend upon voltage, so when the voltage suddenly increases, their value will adjust itself so that there is no damage done to the circuit. So they are used as protective resistors, and there are also other resistors called magnetoresistors. They are used for measurement of magnetic field and things like that. There are plenty of types of resistors which one can study about. Now let me move on to another important concept. The whole of electronics is to be learned by going through very precise concepts which are very useful in the whole application of electronics. What the first concept that I would like you to understand is about the ideal voltage source. We make use of voltage sources by way of power supply or battery, but we should always recognize that each one of these devices, or the power supply or the battery, will also have a resistance of its own, which is called the internal resistance of the device. So any power supply for that matter will have an internal resistance. The resistance in general will be kept to be very small, but there is a finite resistance associated with every voltage source, be it a battery or a power supply, as you have seen. So this internal resistance will produce a lot of problems unless one takes note of it, because whenever I apply the voltage source to a set of network of resistors, there will be a current drawn, and depending upon the amount of current that is being drawn, you would find the voltage drop will be there in the internal resistance of the source, and therefore the amount of voltage available for the external circuit will decrease. This is a very critical important thing that I wanted to explain to you with a simple example. For example, here you assume a 6 volts battery connected to two different type of resistance. For example, two circuits. In one circuit, the 6 volts battery is connected to a 6 ohm resistor. In another circuit, the same battery, similar battery, is connected to 1 ohm resistor. Now, what would you expect the current to be in each case? In the first case, for example, 6 volts by 6 ohms, voltage by resistance gives current. 6 volts by 6 ohms gives me 1 ampere current, as you can see on the screen. In the second case, 6 volts but by 1 ohm, because the resistance there is 1 ohm, you expect 6 amperes to be flowing in the circuit. Now, if you actually put a current meter, as we have done in the earlier case, and measure the current, you would find the current will not be the value that we calculated. I have shown once more the circuit here, and the current that you measure will not be the same as what we calculated using simple Ohm's law, for the simple reason the battery has got its own internal resistance, which is corresponding to 1 ohm. So you find when I draw 6 amperes current, 6 amperes into 1 ohm will when I have 1 ohm along with 6 ohms, the total resistance in the circuit is not 6 ohms but 7 ohms. So 6 volts by 7 ohms is 0.86 amperes, it is not 1 ampere as we calculated because of the additional 1 ohm. Similarly, 6 volts by 1 plus 1 ohm is external resistance, 1 ohm is the internal resistance, together they form only 3 amperes. Therefore, the actual measured current in the circuit will be either 0.86 amperes or 3 amperes. So what is happening? Out of the 6 volts, in the one case 0.86 is dropped across the internal resistance and you have only 5.14 volts available for the external resistance. In the other case, because 3 volts is dropped across the 1 ohm internally, you have only 3 volts available for the resistors that you connected outside. Therefore, you find even though you apply 6 volts to a battery and you assume you are applying 6 volts, because of the internal resistance, the actual voltage applied to the external resistance will differ depending on the actual current that is being used in the circuit or drawn in the circuit. So when you draw more current, more voltage will drop across the internal resistance and therefore less voltage only will be available across the load. The load here is the external resistor that you connect. But ideally, we wish the voltage applied across the load must be equal to the actual voltage of the battery, and this will happen only when the internal resistance of the battery or any voltage source becomes 0. Therefore, when the internal resistance of a voltage source becomes 0, whatever may be the current that you draw by connecting different loads, you would find there is no drop in the internal resistance and therefore there is no voltage variation at the load, and the load voltage will always remain constant. So ideally we would like to have that situation, that is the situation where the voltage source is characterized by 0 internal resistance. So we would see later on circuits which will regulate a unregulated power supply. An unregulated power supply is one whose voltage can change whenever we change the load. So if you want to regulate, that means you want to maintain a constant voltage, then you should attempt to introduce devices in the circuit which will make the effective internal resistance 0. When that happens, you would find this will become a very close to an ideal voltage source. An ideal voltage source is characterized by 0 resistance. In reality, all voltage sources, as I already mentioned to you, will have a finite resistance. Even when I regulate, the resistance will become smaller and smaller, but it can never become 0, as we all know. And therefore, there are no ideal voltage sources in reality, but the resistance of a regulated power supply can be made very small so that for all practical purposes it remains to be very close to an ideal voltage source. Now we have seen different types of resistors in this lecture: variable resistors, fixed resistors, and different types of fixed resistors like carbon resistors, metal film resistors, wire wound resistors, and also we saw the single in line package resistors which are used along with ICs. Nowadays we also have what are known as chip resistors. They are too small even to show to you, they are very small, you have to use a lens to find out, and you will be asking perhaps how they would be soldered. They are soldered by a very careful tiny soldering iron. They can be soldered. There are different techniques for soldering such devices these days, but they are also existing. If you look at any modern circuit board, you would find they will not have any of the resistors that I showed, but they will have more and more of these chip resistors which are very, very tiny in size. Of course, we also saw the different special type of resistors like light dependent resistors whose resistance depends upon the amount of light falling on it. They can be used for detection of light, amount of intensity of light, or any special applications using light operated switches and things like that. Another special type of resistor is the thermistor, which is a temperature dependent resistor whose value of resistance depends on the temperature, and therefore they can be used as for applications in thermometry applications in heat control, temperature control and things like that. We also saw one of the very important fundamental laws in electronics making use of these resistors, which is Ohm's law. We also did a simple experiment I showed you, whereby I showed that voltage is proportional to the current when I have a fixed resistor in the circuit, thereby verifying Ohm's law. I finally talked to you about an ideal voltage source. An ideal voltage source is characterized by zero resistance, and an actual voltage source will have small value of internal resistance. We should always be conscious about this fact that all practical power supplies and voltage sources will have finite though small resistance as part of its internal circuitry. Therefore, there is an internal resistance which is very small, which we have to be taken care of in the applications of different circuits. In the next lecture, we will see about current sources. Just as we have voltage sources, we also have current sources which are characterized by constant current. So, what are the characteristics of a ideal current source, and what are the properties of current sources, and resistors when combined, what will be the effect. For example, they can be combined in different ways. One way is to combine them in series, and another way is to combine them in parallel. So, what will be the effect of connecting resistors in series and in parallel? That also we will see. For example, the parallel resistors will divide current, series resistor will divide voltages. That brings us to a very important application of resistors, which is as potential dividers. So, resistors can be used to obtain or divide given voltages in the appropriate value, appropriate division. Apart from that, we will also see some of the other component. One of them is a capacitor. A capacitor is something which is used for storing charges, and they find very wide applications in different electronic circuits. Capacitors of several applications. There again you get different types of capacitors and different types of special capacitors, which just as we had different types of resistors, different types of special resistors like LDRs and thermistors, we also have different varieties in capacitors. You have fixed capacitors and variable capacitors. All of them are very, very useful in electronics in doing different circuits. Apart from that, there are other components. Again, they all belong to the common category of passive components. Coils and transformers. Coils are basically inductances. They are also used in oscillator circuits and in different applications. Transformers are also very useful for stepping up or stepping down AC voltages, and therefore they are very useful in making power supplies for in electronic applications. And therefore we will see about inductances or coils and transformers, step up, step down, what are the basic functions of the transformers, what are the characteristics of transformers, all those things we will briefly see, and different types of transformers and coils also we will see before we go into the actual application circuits and things like that. We will also see later on about the active devices like transistors, field effect transistors, operational amplifiers and things like that, and then we will also see some other instruments which are being used for electronic applications. Thank you.